So, hello everyone. Welcome to the summary session for geosynthetics and reinforced soil structures for this course run, that is from July 2024 to October 2024. So we have already covered all of the topics that were included in the course, and what we are going to do today is that we are just going to have a brief recap of whatever we have studied in the past 12 weeks. Okay, so this will just be a summary session. We won't be discussing anything new or something different this time, but what we are going to do is that we will be just revisiting whatever we have studied in the past 3 months in this course. So this course we basically started uh, with the basic introduction of what are geosynthetics, what are the different types of geosynthetics and all those stuff. And generally we went much deeper and complicated topics such as the design, not complicated actually, but little bit technical topics, as I would say. Technical topics such as your the mechanism how reinforced soil walls, earth walls work, how what is the mechanism behind the reinforced soil structures, then how to reinforce soil slopes, how to design for reinforced earth walls, how to, okay, all these things we studied. Then we studied different, also prior to that we studied the different properties of the geosynthetics, different mechanical properties, then the uh, flow properties such as the in-plane flow, the cross-plane permeability, all those stuff we studied, right? So what we are going to do, we are going to just have a brief revision of whatever we studied in the past 12 weeks. Just briefly, I will be just skimming through all the topics. That's all, and after that, with that, we will close this course. Right, just basically roughly we will be just discussing this course today, so that we can just recapitulate whatever you have studied, so that it is fresh in your head, right? So that you are able to actually perform well in your exam. Just we will be having a brief recap whatever we have studied. Okay, so let us start. So if we see in the first week, let us see. Okay, let us see. Just a second. Okay, let me just download it. So just a second, I will share a different screen uh, where already I have everything downloaded. Just a second. Huh? I don't know why is it not opening. It should open actually. Just a second. Yeah. So let us see, right? So yeah. So we actually started with some brief introduction, okay, brief recap of some basic problems from soil mechanics, right? We started with some basic soil mechanics. We solved some basic problems regarding our this triaxial tests and all that stuff, right? So we started by solving all these things, and then after that we solved some problems regarding the retaining wall theories, earth pressure theories, the active earth pressure, the passive earth pressure. We solved some problems regarding them, right? Just to recap, then what we did was we introduced this, right? We introduced the types of geosynthetics, right? So what are the types of geosynthetics? We have geotextiles, we have geocells, we have PVDs, we have your nets, we have geogrids, we have geomembranes, we have geosynthetic clay liners, all these things. So by now you already know that for what purpose all these geosynthetics are used, right? So you already know for what are the uses of each of these geosynthetics, correct? So I did not discuss this again. And then we actually discuss the functions, right? So what are the basic functions of all the geosynthetics, such as reinforcement, filtration, barrier, drainage, all these things we discussed. Okay, so this always you should keep it in mind. Then you actually had the types of polymers that form the different types of geosynthetics, right? So polyethylene, polypropylene, PVC, PET, PA, PSO, polystyrene. So all these things are different polymers which actually form your different types of geosynthetics, right? Which are used to manufacture different types of geosynthetics. So we had a look at that. So basically in the first class, this was all that we discussed. We just introduced the topic of geosynthetics, saw what are the different types of geosynthetics that are available, and then we had a basic introduction of how they are actually manufactured, right? And then now let us see to the next, what we discussed in the next week. Right, so in the next week, we introduce the session by recapitulating the triaxial compression test, right? So triaxial compression test, you already know what is a triaxial compression test and what are the different types of triaxial compression test, right? So you have the UU test, you have the CU test, you have the what? You have the CD test. So all these are all the different types of triaxial tests that are available to us, and which is actually used in what cases, that also you should know. And then we discuss the different parameters of the triaxial test and actually how we can get the shear strength parameters of the soil, that is the C and phi of the soil, from the triaxial test results that we also discussed, right? So we have the PQ, we have the P and the Q, then we plot the PQ, from there we get A and beta, from that we can relate to the C and phi, right? Right. So then we saw some results of the triaxial compression test, right? So very easy to visualize. So obviously with the increasing number of layers, what is happening, the strength of the soil, or the capacity of the soil to take loads, that is increasing, right? So at a confining pressure of 25 kPa, you can see that as you increase the number of layers, a higher deviatory stress is reached. It is the soil is able to take more load, that is the reinforced soil is obviously able to take more loads than the unreinforced soil. So this is the unreinforced soil, these are the reinforced soil, right? And one more important thing that you should note, that this peak actually occurs at a higher strain level. Why? Because you actually need a higher strain to actually mobilize the shear strains or mobilize the strain in the geosynthetic material, right? Similar behavior is saying for higher compression, so for higher confining press, you need much higher strain to actually transfer for actually the geosynthetic to take the loads, right? So you can see all this stuff here. So how we can get C and phi from the PQ plots by getting the beta and A values, that also is should be discussed. So this is very important, you should not forget this, and you should actually always remember this. Okay, you should always remember this. That when what how do you explain the increase in strength, right? So you can explain the increase in strength by increasing friction angle or the increase in apparent cohesion. So I am not going to discuss that detail again. So this you should remember, and if you, I hope that you are able to recall that what are the how that this mechanism actually is explained. Okay, so one mechanism is that the increase in friction angle due to reinforcement, and the other mechanism, other way it can be explained, is that the increase in apparent cohesion due to the reinforcement. Okay, then we discuss the failure modes. So what are the failure modes? We have the pull out and the rupture failure mode, right? So all these things we discussed. So this is how we derived everything, and then we saw that when the rupture governs, we have the apparent cohesion that explains the increasing strength, and when the pull out actually governs, at that time the increase in friction angle actually governs the increase in strength. Actually, not governs, it explains the increase in strength. So both of these things we actually discuss. These are all the mechanisms that we discuss. Actually, these are nothing but the mechanisms that we discuss regarding the how the reinforced soil actually behaves, or what is the mechanics involved behind the reinforced soils that was actually discussed in the second bridge. So second bridge actually very important because very like we have a lot of technical stuff that is going here. So you should actually revisit this very nicely, and I hope that you are able to understand all these things. And then we solve some easy problems, so we are not going to obviously discuss the problems again, right? This horseman approach, all these things we discussed, and these problems were also given in your assignments, right? So I hope that you are able to solve the assignments also, right? And then we came to the testing of geosynthetics, right? So why do we actually need to test geosynthetics? That to be understood. So why do you actually need to have a testing, why do you actually need to test geosynthetics? Because obviously as an engineer it is your responsibility that whatever samples you get from your vendor, you should actually test it in your lab and see that whether those whatever material they are supplying to you, those are actually of the specified specifications or not. Okay, so that before you apply that in your project, before you use those materials in your project, you are sure that whatever the vendor has promised that he will supply, he is actually supplying that quality of product or not. Okay, that is as an engineer, that is your responsibility to always check. Else whatever you design, it's of no use, right? If the in the execution stage, if there is some duplicacy in the product or in the material or something like that, there is no use of designing and investing so much amount of money, right? The structure is going to fail. So as an engineer, it's your responsibility to ensure that the product that you are using in your site, it's of the correct specification. That's why you should have knowledge about the types of tests you need to do and all the properties of the geosynth. So initially then we studied about the properties of geotextiles, right? So these are the basic properties of geotextiles. I am not going to repeat this again, so just you can see here physical properties, we have these physical properties. All those things are actually discussed in much detailed, was discussed much detailed in the class, in the main lectures. And I also suggest to you that you please go through the books. Okay, please go through the books, book any geosynthetic books. I will suggest you go to the book by Professor Robert, Dr. Robert Corner's book, Robert M. Corner's book, and that book is really very good. And so there everything is given in detail, and I suggest that you should go through that book. Then we saw some videos how these tests are done: trapezoidal shear test, rep tensile strength test, all these things we saw, right? Then CBR, this puncture test, all this stuff we saw. Right, then we have the hydraulic properties, as I said, the apparent opening size, cross plane permeability, in plane permeability, gradient ratio test, long term permeability, all this we discussed, right? What is the cross plane permeability? The cross plane permeability was this permeability. So this is the geotextile, say, or geosynthetic. So this permeability in this direction is nothing but the cross plane permeability, and the permeability in this direction is the in plane permeability. So this in this direction, it is what the function that it is offering, that is the drainage function, and in this direction, if we are considering, that is the filtration function, right? So cross plane permeability, in plane permeability, all these things we here discuss. Okay, so there are various filter criteria and all those things. I am not going to repeat it again, right? So for cross plane permeability, we have this parameter called permittivity, psi, right? We have this parameter called psi, which is nothing but the cross plane permeability. And for the in plane permeability, we have a parameter theta, right? Transmissivity, that is the theta. So we saw what the reason. So this is the theta that I was talking about. Then we studied about, then we solved some problems regarding this in plane permeability and cross plane permeability, right? Then we saw some videos regarding the testing of geogrids, how geogrids are actually tested, same similar to geotextiles. Okay, there are very much these details actually you should actually remember. Okay, you should not forget. Okay, so now let us see the next week what we did. So we introduced the retaining walls. Okay, we introduced retaining walls in the third week. We saw why retaining walls have to be, you already know, right, why retaining walls have to be used, why are they actually used. So we have different types of retaining walls: gravity retaining walls, cantilever retaining walls, okay, counterfort walls, all these retaining walls we have, and already you know about all these things, right? So we saw what are the different types of retaining walls, right? So these are buttress walls, as I say, counterfort walls, buttress walls, and these are what, these are called your uh, sheet pile walls. Okay, these are sheet pile walls, are steel piles, that are steel sheets that are actually driven into the soil to form this wall like structure, and then they are braced from inside. Okay, so easily what you can do, you can do some digging and then construction inside it, so that the soil from outside won't actually interfere in the work that you're doing within that section. Then we have anchored walls, where the water wall is anchored into the soil. These are bracings that are used, all these things we saw. Then we saw this reinforced wall, so we have some facing, then we have reinforcement. Okay, then we have nailed structures, nailed walls, where we nail the wall with steel nails, iron nails, and then we we shotcrete the facing, right? We anchor the nails here and then we shotcrete it. All these things we discussed. Then types of retaining walls, yeah, that similar, uh, right? So these are the same reinforcement. Yeah. So now then we discuss the types of reinforcement that we can use to design a or to construct a reinforced earth wall. We can use geotextile. Even geotextile we can use geogrid. We have inertial, biaxial, triaxial geogrid. Then we have geocells that we can use to construct retaining walls, reinforced earth retaining walls. Okay. Then we can use steel, okay, steel strips or steel meshes also we can use. So there are various options that you can use. So it depends upon the engineer to decide whatever it's suitable, based upon the cost and other factors, what environment you are constructing the wall, all those things you have to consider, and then you have to design what reinforcement you are actually going to use. Okay, so we have these various wall configurations where you have this equal length of geosynthetic reinforcement that is there, or different lengths at the bottom and the top. Then you have the double face thing. So these are the various wall configurations that you can have. So what are the components of reinforced soil walls? You have this leveling pad at the beginning. Okay, this is the foundation soil. You have the leveling pad. Then you have the facing panels. Then you have the reinforcement. Then you have the reinforced soil. You have the backfill soil. Okay, so all these are the basic components of the reinforced soil retaining wall system. Then we saw a detailed video, right? We saw a detailed video where step by step it was shown how a reinforced soil wall or reinforced earth wall is actually constructed in the field, right? We saw a detailed video. Okay, so we saw a detailed video step by step how we constructed reinforced soil wall in the field, that we actually saw. So these are the different codes and standards for reinforced soil retaining wall design. Right, so what properties should the backfill soil have? So the backfill should always have a granular soil. So always choose the backfill soil as a granular soil, high frictional, high friction angle value of the nodal. So that means that inherently the soil has higher strength, right? And obviously, if it has higher friction angle, obviously the interface and friction angle between the reinforcement and the soil, that is also going to be high, or that means it is going to be higher pull out resistance capacity, right? So higher phi means higher delta. Higher delta means what? Means higher pull out capacity of the reinforcement, right? So obviously it's our target that we should we should always use a granular soil. Okay, then we briefly discuss the lateral earth pressure theories. So we have the lateral earth pressure theories that you already know: active earth pressure, passive earth pressure, and that is basically given by Rankine's theory, and later it was modified by the Coulomb's theory, right? So all these things you already know from basic soil mechanics. Then what are the design loads that we should take? The self weight of the structure, live load, crash barrier load, seismic load, all these things we should consider. All the stuff we discussed. Then we have stability calculation. So these are the external stability calculation, stability that you have to consider. The external stability that you have to consider. So you have the sliding stability, the overturning stability, and the bearing capacity, right? So all these three are the basic. And apart from that, you also have the slip circle failure. Okay, the slip circle failure that you also should consider, or you should also check while you design a reinforced structure or reinforced earth structure. Okay, so sliding stability, overturning stability, bearing stability, and slip circle failure. And what are the different load combinations in different scenarios that we saw, and then we solve some problems, right? So basic problems from your basic retaining wall earth pressure theories we solved. Nothing different. Yeah, all that's all. So here we, in this week, in the fourth week, we actually solved some problems regarding the stability calculations and all of that stuff, right? So we have external stability analysis, like lateral sliding, overturning, bearing capacity failure, and overall failure, right? So uh, yeah, so how to check for lateral sliding? We saw you need to consider all the lateral forces coming. So what are the things that are contributing to the lateral force? So one is the active earth pressure from the backfill soil. Then we have the active earth pressure coming from the surcharge load that is there, the permanent surcharge load, and obviously from the live load of the vehicles that will be traveling, we say the vehicles that are going, so that live load also you have to consider, and also the crash barrier load. Okay, so these are the various loads that are taken considered in case of this horizontal load, okay, which is required for checking the factor of safety against sliding. And while calculating the resistance force, the force that resists this sliding, that is given by this. So here you can see that the live load is not considered. Okay, the live load is not considered, only the dead load is considered. Okay, and the minimum factor of safety against sliding should be is 1.5. So the factor of safety you have to ensure that is more than 1.5. Okay, so this is the factor of safety against sliding. Then we have the factor of safety in overturning. So the similar loads you have to take, and the lateral force you have to calculate the moment, and those lateral forces are going to generate an overturning moment, right? So that moment you are calculating, and again you are calculating the resisting moment also, and the resisting moment overturning moment will give you the factor of safety is overturning, and that should be at least greater than 2. Okay, at least it should be more than 2. Okay, so these are very easy, right? Very simple, and I hope that you have understood this. If you have any doubt, you can ask me anytime. Okay, and but these are quite easy. I'm hopeful that you have understood, but nevertheless, if you have any doubt, please feel free to ask me. Then at last we have the bearing capacity check. So the bearing capacity of the foundation soil should be strong enough to take the high enough to take the load that is coming, right? So that we actually found out. Okay, so bearing capacity check, you already know what are the types of bearing capacity failure. You have the general shear failure, local shear failure, you have the punching shear failure. Everything is given in detail in IS 6403, and you always use IS 6403, the Indian standard 6403, to calculate the bearing capacity of any soil. And of course, remember to always check the settlements, and check the pressure corresponding to the permissible settlement also. Okay. Then at last we have the overall failure that we are saying, that is a slip circle failure. And to check that, what you can use, there are various methods that can be used to check this. So the most common is this method of slices. Okay, method of slices, that is that you divide the soil into various slices and then you cut the slice into various wedges, and then take the limit equilibrium of the that wedge by equating the forces, and then you find out the total factor of safety. Okay, so this is actually very difficult to do by hand, right? So because you have to take many slices and then many wedges, and the minimum, the slice that gives the minimum factor of safety is the factor of safety of the whole system, right? So there are various programs, computer programs that are available that are available which you can use for this purpose. That we have the seismic loads, how to incorporate the seismic loads we saw. So this is the response spectra. So one interesting thing that I think has, so you can see that for soft soil, so say you, so this I hope that you understand, right? I hope as civil engineers all of you must have used IS 1893 to uh, during the seismic, to do the seismic design of any building, right? And I am sure that obviously each one of us have done at least one building design during your bachelor's days, right? During your undergraduate days, I am sure that I am hopeful that you have done at least one building design, okay, one design of a whole RCC structure where you have used this IS 183. And if you have not used, it is not done this, it's actually really unfortunate. Okay, it's really unfortunate, and you should actually really consider calling yourself civil engineers. Okay, but if you have done, it's very good, well and good. If we have passed your bachelor's degree, you should have done this, used IS 1893 in your what in your while designing the RCC structure. Okay, if not, it's like really, what to say, it's really sad actually. So this is nothing but the response spectra, right? This is the response spectra, and for a certain time period, you can see that these are the spectral acceleration coefficient. Okay, acceleration coefficient of a certain area. Okay, certain area you can say. Okay, response spectra. So for a certain seismic zone, so for the response factor, what? So for the so first we take out, calculate the period of the structure, right? So from the period of the structure, what we can do, we can get the uh, acceleration SA by G. This SA by G, this is the acceleration coefficient that we can do, and that acceleration coefficient is actually used here, SA by G. Now you can see that as we have soft soil, so for same time period, for soft soil the SA by G value is higher than that from the hard soil. Why it is that? So in what happens when the seismic waves actually travel from the base rock to the surface, and when that, while traveling, it passes through some soft soil, what happens, there is some soft soil amplification that is seen. Okay, there is some soft soil amplification because uh, there is a change in the velocity, change in the velocity of the shear waves. Okay, there is a change in velocity because in stiff material the velocity of the shear wave velocity is higher, and in the your last your, what to say, in your stiff, in your hard, uh, in your soft soil the velocity is quite low. And what, that's why what happens when the shear seismic waves actually travel from soft to hard, sorry, from hard to soft, the velocity reduces, the shear wave velocity reduces, and due to that what happens, there is a large, that the magnitude of that increases, and that actually so this is actually known as the soft soil amplification. Okay, due to that you can see that this spectral acceleration actually increases. All right. So this response spectra, what I can say, this is so this is given in I81893, so this we can use for India, right? But nowadays there is some seismic microzonation is also given. So for a particular location, particular site, but your specific site, you need to develop your own response spectra. Okay, so that you can analyze. So that is more. All right. So this is, so you can, this is the seismic zonation map that you have. Okay, The northeast falls in zone 5, then you have Delhi in zone 4, all these things you can see. But just give me 1 second. Huh? Yeah. So this is how you need to include the seismic loads in your load calculation. Okay, this is how you need to include the seismic load. Okay, in the your lateral pressure while calculating your factor of safety. Okay, this is one more important method which is known as the Mononabe-Okabe method to get the seismic coefficient. Okay, the seismic earth pressure is actually given by this active earth pressure is the active earth pressure coefficient, and then from there we can actually get the seismic dynamic component of the seismic force that we can actually get. This is the Mononabe-Okabe method. So this is actually a pseudostatic approach. Okay, the soil is actually considered to be rigid, and it is considered that from bottom to top in the soil obviously equal accelerations are uh, there. The structure is considered a rigid structure, and then you are actually developing this. So this is a pseudostatic approach. So I'm not going into this detail, but if you are interested, you can there are many papers available, you can have a look at that. So germination of the seismic earth pressure is itself is a broad research area. Okay, so if you want, you can have a look at those things. Then all this stuff, then this was all about the external stability, then you have the internal stability. So the internal stability is nothing but two things we have to consider, right? So one is the rupture and one is the pull out. So two of these things you need to consider, and apart from that, third important thing that you need to consider is that your connection strength, the connection between the facing and the reinforcement, that also should be strong enough. So all these things contribute to the internal stability. So always you should check that there is no rupture failure, there should not be any pull out failure, and there should not be any connection failure. Okay, then long-term reliable design strength, how to find out the reliable tensile strength, you know, obviously by dividing with the reduction factors you found out. So this I am not discussing again. Okay, internal stability, how to calculate the internal, how to do this internal stability calculation, how to find out the length, this length comes out from geometry, and this length comes out from this pull out load, right? So this we calculated already, and minimum this embedment length should be 1 meter, if you recall. So all these things we studied. So this part is very important, right? So week 2, week 3, week 4, these are very important. So you should have a good nice look, have a study this portion very in depth. Okay, so now I'm not repeating this again and again. So you have internal stability, all this. This already you know, we have studied this, right, while designing. Let me just go down. Yeah. So as I was saying, minimum embedment length, you should have 1 meter beyond the ruptured plane. How to calculate all these things we already did. Right, so this is the check for pull out resistance. Okay, go to the problem. Pull out test, all this stuff we studied. Let me just the problems we solved about the stability calculation. Yeah, yeah, okay, in the 5th week I think. Okay, let us see the 5th week. In 5th week I think we solved some problems regarding the design of reinforced earthworks, right? Yeah, so this was the design problem. So let us see this, huh? So what we are asked to design a 6 meter high wrap around geotextile wall. Okay, so what was the first thing that we did? First we determined the horizontal pressure as a function of any depth. Okay, any depth from the top, we determine the horizontal pressure. So first we have the Ka, that is the active earth pressure. then we have the total horizontal pressure, the active earth pressure, and then from the surcharge. So both we added, we got the horizontal pressure, right? Then we got the T allowable. T allowable is what the ultimate tensile strength divided by the what? Divided by the reduction factors. We get the allowable, tensile strength. Okay, we will get the allowable tensile strength. Okay, then a load coming on each reinforcement obviously should be less than the T allowable to prevent the rupture. Now, to how to find out the spacing? The spacing is going to actually satisfy this criteria. Okay, so spacing times the horizontal pressure is equal to T allowable factor of safety. From there, we get a function of the spacing in terms of the depth Z. So for depth z equal to 6 meter, you have spacing of this much. By trial and error, we then decide the spacing. Okay, then we decide the spacing. So this is the basic arrangement that we decided the start. So 9 layers we can have 300 mm spacing, then 4 layers 500 spacing, and 2 layers is 350 mm spacing. Right. So this was how we decide the spacing, and the spacing actually helps in satisfying the rupture criteria. The spacing actually helps in satisfying the rupture criteria. Now next we have the pull-out criteria. Now to satisfy the pull-out criteria, that will be actually satisfied with this embedment length. The embedment length, we calculate the embedment length by this spacing times the horizontal pressure etc. safety by 2 times, because you have two surfaces top and bottom, so the friction resistance of both the surfaces of the geotextile will be coming into the picture. So we have this factor 2 here. So this divided by this, then we get the LE in terms of SP. Now LE, the total length of the reinforcement is what? LR plus LE. So LR is what? LR is coming from the geometry of this triangle. So this is 45 plus 5 by 2 because it is the active failure wedge. So from there we have the LR, and so LR plus LE is 50 by total length. So now what we do, we finally make a table, right? So in a tabular format we do to solve the problem. So this we had done it together in the session, live session, right? So I hope that it is clear to you. So at various depths we have, then we calculate the SV, then we calculate the LE, then LE minimum we have to minimum take 1 meter. So LR, then we calculate calculated is nothing but see LE and LE minimum, we are having LE minimum as higher, so this plus this 3.72, like this we have the L lengths of the different layers of calculate. Then what you can do, then we can decide the total length. So this to this much you can give 2 meter, this one you can 3, it is up to you. Okay, it is up to your discretion how to design thereafter. Okay, then also you have to check for the overlap length, because in this out of plane direction you have to have some overlap between the geosynthetic, right? So that also you have to decide. So how to calculate this overlap length, that also we checked. Okay, so this was all about the internal stability. Now after the internal stability, what you need to do, you need to check for the external stability. External stability means what? The sliding, overturning and the bearing capacity. Okay, so these are the properties of the backfill soil, these are the properties of the foundation soil. So now we find, similarly we find out the KAP, then factor of safety against overturning. This I am not going into detail. So this how, please if you don't recall, please see the recorded videos which I have uploaded. Okay, there how to take these weights and moments, these I have discussed in detail. Okay, you can have a look at that, that will be helpful to you. Okay, so we have the overturning, then we have the sliding, all these things we have, right? Okay, then we find out the factor of safety is sliding and overturning, and we check that these are acceptable here. Okay, overturning, and this is the sliding. And then bearing capacity check also you have to do. So these problems we solve not considering the seismic forces. Okay, so what you can also include the seismic forces and then solve the problems, that also you can do. Okay, then similar problem we solved again. Okay, so here we have used metal strips instead of geotextile. We have used metal strips to design this reinforced earth one. Okay, so that this problem we solved. So similar, first you have to satisfy the internal criteria, then you have to check for the external stability. So the same thing we did. Okay, I'm not repeating this. You can, if you want, you can see the videos. Okay, so this was all about this. So again in the 6th week also we started by solving a similar problems on reinforced earth wall. So we solved problem using geogrid. So first problem was wrap around geotextile. Second problem we solved was with the steel strips. Third problem, this problem is from this by using geogrid reinforced wall. Okay. Just a minute. Just a minute. Yeah. So yeah, this problem is also quite similar. See, you can see we can found out the T required, the level strength, required strength, all those things we did. Then we checked for the external stability, same overturning and your sliding stability check, overturning stability check. Both of these things we did. Bearing capacity check, that also we did. Then we did the internal stability check. Okay, so in that this problem actually everything was given to us. Just we got to check that stuff, right? So we checked that. Right, we checked all these things and then finally we decided the length of the reinforcement. Okay, same process, just a little bit different in the material, difference in the material in the spacing and all those things, but rest everything is quite similar. Okay, problems are quite similar, quite easy also, right? You don't have to memorize this, right? It's a very easy problem, just basic steps you need to follow, what we need to do, what we actually need to do, and easily you can actually easily solve the problem. Okay, so this is not that tough. Okay, not that tough, these are quite easy problems, so don't get afraid of the problems. These problems are actually a little bit lengthy but very easy, a little bit lengthy but not that tough. Okay, so still if you have any doubt, please feel free to ask. Again and again I am saying, if you have any doubt, please ask me anytime. Okay. So how to design as an embankment or a wall? So for a steeper slope, say steeper than 70 degrees, we design it as a retaining wall, and for shallow slopes, we design it at a design as a slope, right? Design as a slope. Okay. So you have embankment, say so embankment, the slopes of embankment too steep. Then we design it as a design the slopes as a retaining wall, and it is less steep, shallow slopes. Then we design it as a normal slope. Okay. Now, see, one important thing is given, which shear strength properties you should use. Okay, so either use the peak or the residual. Okay, peak or the residual. Residual means the constant volume. So generally, the slopes undergo large deformation, especially those on the soft soil. So base there is a soft soil, and above that you have a embankment, right? So what happens? The embankment undergoes large deformation. So due to that, generally we use the constant volume shear strength. So the shear strength parameters calculated using this value. Generally we use that instead of the peak. Okay. So design of the basal reinforcement. Basal reinforcement means this reinforcement that will provide the base of this embankment. It is known as the basal reinforcement, and that basal reinforcement is actually used to for the initial construction of the slope. So how to design that we saw, how to calculate the factor of safety. Okay, then so here this is for the cohesive soil, right? Cohesive soil directly Cu into L into R, that you can do. But say you have a C5 soil, in case of a C5 soil you need to have this wedges. Okay, you have to make wedges and then you have to do slip circle method. Okay, you have to do you have to do the slip circle analysis. Whether you have a C5 soil or only 5 soil, you need to consider only this slip circle analysis. And for only C soil, it is only cohesive soil, you can directly do this. Okay, directly C times this arc length you can do, and like that you can find out. Okay. A factor of safety you can find out like that, so I'm not going into depth. So analysis for steep plus similar, these are for planar analysis, where rather than taking a slip circle you are just considering a wedge, straight wedge, planar wedge you are taking, and then you are calculating the factor of safety. So this problem was very easy, directly all the values are given and directly you have to find out the factor of safety. So I am not repeating it again, quite easy problem. Okay, so this problem was all about, so we discussed one this method, right? This Jewel's method on how to decide the reinforcement length of the for reinforcement for designing of reinforced slopes, how to design the, how to choose the length of reinforcement and all. So this Jewel's method is a graphical method that we can use. So this also we use to discuss that how this also we use to choose the length of the reinforcement, or we use to design the retaining wall, right? So not retaining wall, retaining reinforced slope. Okay, so this Jewel's method is a very direct graphical method that you can use to design steep reinforced soil slopes. Okay, steep reinforced soil slope, you can use this Jewel's graphical method to design the reinforcement. Okay, for steep reinforced soil slopes. That also we solved some problems regarding that also. So we have covered everything. Okay, we did not leave a single thing. We solved problems for all the topics. Okay, we covered a wide array of things, and you have a lot of question bank ready with you already. We have the assignment problems, we have the problems that were discussed in the class, we have the problems that was discussed in the interactive sessions. We have a lot of problems, so I suggest that you please go through these problems again and again. Try to understand the basic concepts. The basic concepts should be very strong. You should not forget the basic concept. Whatever problem comes, your concept should not be wrong. If your concepts are correct, basic your mechanism, how what we have to do, what how everything is happening, that basic knowledge is correct, then any problem comes you can solve it very easily. Okay, so I suggest that you go through all the problems very easily rather than just looking over the steps. Just see what is actually technically what is actually happening within that. Okay, that you can that I suggest you to. Okay, so now let us see. We don't have much time, so let us see. We'll just go a little bit faster now. Just download everything. So here again we solve one problem from Jewel's method that we discussed. I'm not going into it again. Okay, so please see, so look at this problem. Okay, if you don't remember, you can always refer to the videos. Okay, those recorded videos are already uploaded by me. Okay, and the links, you already have the link, so obviously you can anytime you can refer, have a look at those. Okay, right. So then we saw designing with geocell. So say you have a embankment. Okay, embankment over a very soft soil, and below that you have firm soil, very soft soil, and then of the top you have the embankment. So in that case, how to construct the embankment, what you can do to strengthen, how to construct the embankment in that case, what you can do in that case, you can use the geocell. Here in this level you can use a geocell. Okay, so they are designing with geocell, everything we discussed in detail. Okay, the designing is actually based on the slip line method by Jenner et al 1988. So this paper, you can have a look into this paper in detail, everything is given. Okay, how you can do this, you can see, because this method of slip line method and all these things are, this is a little bit advanced topic, so you might not be knowing this in detail, but still what I suggest is just have a look at this. The basic understanding you should know, means how at least you should know that there yeah, this method is there, with this we can actually do this thing, so that knowledge you should actually have. Okay, so I am not going to detail, so everything was discussed. Just go through these notes again and again. You can go through this paper, this paper is also very good, and everything is given in detail regarding designing of geocell reinforcement for supporting embankments and software. Okay, go through this paper. Everything is written very simply in simple words, very nicely. You can have a look. All right. Yeah, what is next? What do we have? Wait, just a second. Yeah. Yeah. So I'm not repeating this problem. Yeah. Then we discussed an extra topic that was unpaved road as we had time. So I thought that I will just introduce this topic. So in this we saw that with the use of geosynthetic, with the use of geotextile, what we are able to do, we are able to reduce the thickness of the or the quantity of the aggregates that are required to construct an unpaved road. Okay, unpaved road. So what are unpaved road? Unpaved road are nothing but soft soils. Subgrades have sand, we have a subgrade, soft soil subgrade, and over that directly we have stone aggregates placed over it. So that is the unpaved road. So unpaved road generally say it requires a thickness of 100 mm, and if you use a geosynthetic or we use a geotextile layer, the thickness of the or the quantity or the thickness of that aggregate that is required to construct the unpaved road reduces from 100 mm say to 50 mm. Okay, so this reduction in thickness, how much reduction in thickness actually happens, that we calculated in this topic, right? So see, you can see initially it is h naught, this thickness. With the use of a geotextile reinforcement, it is coming from h naught to it reduces to h, right? So all these things, so this is not required for the exam, so I am not repeating this. That's the basic topic, extra topic that I discussed, that you just for your knowledge, that you should actually know the mechanism. I discussed everything, so I am not repeating it. Let's see the next thing. Yeah. Yeah, then we have foundations, right? So how we can improve the bearing capacity of foundation? Obviously, if we reinforce the soil, we can increase the bearing capacity of the soil, right? So it is obvious, it is very intuitive. So how to do, what are the basic parameters? So there are, what are the, this I am not repeating again, these are from a basic soil mechanics, right? Then this what to say, yeah, you have a footing, so right, so you have a footing, so with the footing we reinforce the soil. Below that in layers we put geotextile or geogrid or what, or steel strips, maybe steel strips, anything you can put. So with that what happens, the uh, bearing capacity of the soil increases, and that is actually defined by the bearing capacity ratio. The bearing capacity of ratio is nothing but the bearing capacity of the reinforced soil to the bearing capacity of the unreinforced soils. Okay, so all this mechanism we discussed, right? So also you can use a geocell mattress to increase the bearing capacity. So I'm not going into detail. So this is the improvement factor of the bearing capacity ratio is nothing but the Q by Q naught, and again you have the settlement ratio S by B. So there we have various plots. We saw that with increase in reinforcement, the bearing capacity is also increasing. So what are the basic important points that you should be considered? This you should remember: the first layer, where you are placing the first layer of reinforcement, right? Below the foundation footing, that you have to consider the number of layers of reinforcement, length of reinforcement, vertical and horizontal spacing, uh, all this stuff. Okay, so these are the possible modes of failure, the mechanism that we discussed. I'm not going to repeat it again. It will be a very long discussion. If you do not understand, again I'm saying you can contact to me anytime. Okay, so this is the theory given by Bickett and Lee. This is the basic theoretical analysis procedure, one of the most famous papers that was given by Bickett and Lee, which describes how we can we can design this, we can increase the bearing capacity of foundation using your reinforcement. Okay. Okay, let's not go into detail. I will not go into detail all this stuff we do already. Also, what we did, we solved some problems, right? We had solved this problem, design a strip footing to carry a line load, how to design that. We had done this. Okay, everything we made this table we did. So if you don't remember, you can see the video, so I'm not going to repeat it again and again. Yeah, so yeah. And what did you do in week 9? Week 9 we discussed about accelerated consolidation. So for accelerated consolidation we can use sand drains or the PVDs. So that we discussed, right? So that we discussed. I'm not going to repeat it again and again. So we solved the problem where we found out. So you can see for vertical drainage only 17% of the consolidation is happening, right? And if we use the sand drain, higher amount of, so you can see if we use the sand drain, you are able to get almost 90% consolidation in the same time frame. Okay, so this is the benefit of using accelerated consolidation method such as your sand drains, right? So again we have one more thing similar to sand drain, that is called the PVD or the prefabricated vertical drains. Okay, I'm not going to repeat it again. So there are various things. So from using PVDs also we solved this problem. Okay, we decided the spacing, and also there are things that you should consider, that is the spacing and all this, spacing and the pattern, how to choose the pattern, all these things we had discussed. I'm not going to repeat it. And then obviously you have the vacuum consolidation, is another accelerated consolidation process where we apply vacuum to accelerate the consolidation process. And there is one more benefit of this vacuum consolidation, is that the consolidation it is isotropic, because isotropic all around if you take in a soil section, all around the soil section there is same increase in effective stress. Okay, and the effective stress is actually independent of the depth, at all the depths you have the same increase in effective stress, so that is very much beneficial. Okay, so these problems, this mechanism we saw. So actually how this vacuum consolidation works, I'm not going to repeat it. Then we saw stone columns. So what stone columns are, what are encased stone columns, right? The basics you know. And how in what is the mechanism, how encased stone columns actually are better performing than normal stone columns in taking the load. How that happens, it happens due to the confining pressure of the confining effect of the encasement, right? And what is that mechanism, that was given by Henkel and Gilbert. So that is actually given here. Okay, I'm not going to repeat it again. Yeah, so that's all. Then we saw how to design a stone column. Everything is given in IS 15284. You can go through it. Okay, so then we solved one problem. So I told you to ask this from the course instructor, and I hope you have asked this. All the stuff I notes I had given that you ask you to ask. So please verify this from the course instructor. All these green things that I've written here, I'm not going to repeat it again and again. Right. So this was all. Then let us see the 10th. 10th, 11th, 12th, nothing. 9th, I don't think anything much was there. Uh, so in 10th we, yeah, 10th we actually solved about the filtration, right? So how to design a filter, how we can use a geosynthetics, especially a geotextile as a filter that we saw, right? We have the retention criteria and the permeability criteria. So those two criteria has to be followed. So all these things we discussed. Very simple. This part is extremely simple, right? This retention criteria and all those things. So there are various criteria that are given, so you need to choose the appropriate criteria. Then you have the gradient ratio test. Okay, what does this gradient ratio test do? The gradient ratio test actually establishes the compatibility between the soil that you are using and the soil and the filter material, the geosynthetic geotextile that you are going to use. Okay, that develops the, it ensures that there is a compatibility between them. Okay, that you have to ensure by doing a gradient ratio test. Okay, so all these are given, then we solve these problems where you have a rotating wall, behind you have a filter that is given here that prevents soil to enter, all these things we do. We calculate first, the first step is always to calculate the flow. From the flow we calculate the permittivity, then we can find the allowable permittivity of the geosynthetic, and then we found out the factor of safety. So this is how you to do that. This is how you need to do for the permeability flow criteria. And then of course you need to also ensure the retention criteria. What does retention criteria means? Retention criteria means that the soil should be retained and the water should pass through the geosynthetic, so that also you should ensure. Okay, similar problems we solved, right? Right, and then after filtration we studied the drainage. Drainage means what? In drainage what happens, say this is the geosynthetic, the in plane flow, the geosynthetic should carry the water, carry the fluid through it, through its plane, and then drain out into, say, under drain, fluid or liquid, whatever, liquid or gas, whatever. So we have mostly for drainage purposes you have a geonet core, and then which is sandwiched between two geotextile. So this is the basic uh, thing that we have. So the geonet serves as a drainage, and the geotextile that is put at the top and the bottom of the geonet, that serves as a filter. Okay, so we have in-plane drainage capacity. How to determine that? We have the constant head test, which helps in calculation of the transmissivity of the reinforcement. Okay, so all these things are the various reduction factors. Then we solve some problems. Let us not repeat these problems again. You can always refer to the previous to the recordings. Okay. So basic, very easy and very simple problems we solve. These problems related to drainage and filtration are extremely easy, and you can actually easily solve it. Okay, it's not that tough. Just have a quick revision. Just try to solve these problems again by yourselves, and you should be good enough. These are very easy. The main thing where you should put some little bit effort is the problems related to your reinforced earth wall, reinforced slope, then bearing capacity improvement. This part you should actually put a little bit more effort. These problems regarding drainage and filtration is quite easy part. And that design part regarding your reinforced earth wall, it is little bit technical, so you should put more effort in that. Okay, and this thing I think it's very quite easy for you. Okay, so let us to the next one. Yeah, so 11th what we did, same, nothing much. We discussed about the erosion stuff, what are the various erosion control techniques that we have, right? All these things, nothing much. Okay, then we discussed about sustainability, sustainable geosynthetics we discussed, and we solved some problems regarding erosion control structures. These are also nothing but related to filtration and drainage only. Okay, mostly filtration, so that also we solved. Similar problems we solved, so please go through these problems. Okay, and yeah, and in the end what we did, and in the previous class, it is on Tuesday, we discussed about the landfills. Okay, landfills, how, why are landfill covers used, how are landfills constructed, how are geomembranes placed, all these things we did in the Tuesday session, if you remember. Okay, so it's really fresh, so I think I don't have need to repeat it again and again. So please pay attention to this, how we calculate the thickness of the geomembranes, how, what is the mechanism, how we do everything, that then what are the different properties, what are different tests, water vapor transmission, permeance, diffusion, and permeability, how to obtain that we discussed. Okay, so all these things, please have a look at that again. Okay, we discussed many things in the previous class, right? Then how to determine, I was speaking of how to determine the thickness of the geosynthetic. Okay, that how we take the component, how it distributed, then we take the equilibrium, and then finally find out the thickness of the geosynthetic geomembrane. Okay, Please have a look at this. Right, then we solve some problem. Then for a slope, in a slope, if we have a geometry in infinite and finite slope, then how to find out the factor of safety that we saw. So we have an infinite slope, then we have a finite slope with uniform thickness of soil over it, then we have a tapered thickness of soil. So three cases we discussed: infinite slope, and then finite slope we have two cases. So all these things we discussed. Yeah, then we solved this easy problem, this basic formula based problem. Right, and then we saw this run out trend. So this geomembrane is actually placed like that, right? So you have a run out length, and then you can also have a trench where you can actually anchor the geomembrane. Okay, so that it does not comes out of the slope. While you make this your landfill, you can have a long run out, and then you can have a trench also. These are both two different cases. So in these cases, how to find out this run out length, this LR naught, how to get this LR naught we saw, then how to get this LR naught, then this depth of trench, this DAT, how to get this depth, all these things we actually discuss. So there are many formulas in this, so I have given this first. What I suggest is that please go through Corner's book, Robert and Corner's book, and please get the right study this, like see the expressions in the book. Okay, because I wrote it very fast in the class there, so there are high chances that there might be some mistakes while writing the expressions, because these expressions are quite big. Okay, these expressions are quite big, not this these expressions and the previous here in the calculation of these expressions. Okay, why that we used to calculate the factor of safety in tapered case and all those things. So these expressions are quite extensive expressions, so I might have made some mistakes while writing. Okay, there is no guarantee. So what I suggest is that please see the expressions in the book, so refer to the book and then study. Okay, refer to the book while studying, then that will be like very better. Okay, so that was all about this course, so nothing else. So I think we have covered everything, we have covered a lot of stuff. Okay, so just go through each of the topics one by one slowly, revise slowly topic by topic, start from basics, types of geosynthetics, then study about reinforced, how what is the mechanism of reinforced soil, and study about reinforced earth walls, how to design that, and study reinforced slopes, and study reinforced embankment bases using geocells, then study your what these flows, drainage and filtration, then geomembrane, how to use geomembrane, how to determine thickness of geomembrane, then bearing capacity, how you can improve all these things. So slowly you go step by step, you do your revision. Then I think that will be sufficient for your exam. Okay, because you have a lot of problems, we already have solved together a lot of problems in this interactive session, and over that in the class also a professor has solved it, and you got many assignment problems also, so you should be good enough, comfortable enough. Okay, and so thank you so much for attending, and I hope that you had a very nice enjoyable course. And if you have any doubt, please feel free to write me or contact me and stop and ask me anytime, and I will be more than happy to help you. Okay, you have my email ID, I provided it to you in the first class only. Okay, so please feel free to write to me. I will be more than happy to answer your queries, and all the best for to those who are preparing for the exam of this course. I hope that you do well, and thank you so much for attending this live seeing the lectures, attending this live discussion sessions, for solving the problems, solving the assignments. Thank you for attending this course, and we hope to meet you some other days in some other course next time. Okay, so thank you so much for attending, and if you have any doubt, you can ask me, or else we will end the session. Okay, so thank you so much, all the best for your exam, and have a very good evening. Okay, enjoy.